Namaskaram. Today we will discuss partial derivative in multivariable calculus. Before moving to partial derivative, first of all we are going to consider a function of one variable y is equal to f of x. Then we know suppose this is our function, we consider a point x naught. And what is dy by dx at x equal to x naught? This derivative means it is the rate of change of y with respect to x, because here y is dependent, x is independent. Y depends only one variable x. Okay, then can analyze what is the rate of change of y with respect to x. That is the meaning of dy by dx. And this dy by dx has one more meaning. Suppose you consider a tangent at this point, then this dy by dx at x naught gives the slope of this tangent. These are the two interpretations of derivative for one variable case. Okay, we consider a function z is equal to fxy. Now this z depends two independent variable x and y. Okay, it's a multivariable function of two variables x and y. And we know that the z equal to fxy represents a surface in 3D. Okay. Similar to this x naught in one variable calculus, we consider a point in 2D, that is x naught y naught in the domain of f. Okay, but here our z depends two variables x and y. So we can find the rate of change of z with respect to x. Similarly, you can find what is the rate of change of z with respect to y. Okay, so the technique is whenever we find the rate of change of z with respect to x, then we will treat y as a constant. Similarly, if you find the rate of change of z with respect to y, then by keeping x as a constant. Okay, so our aim is to find the rate of change of z with respect to x at this point. Okay, at this point means now we are going to treat y as a constant. What is y at that point? Y naught. So we consider the intersection of the surface z is equal to fxy and y equal to y naught. Y equal to y naught is a plane in 3D. Okay, so what is the intersection of y equal to y naught and z equal to fxy? That is nothing, that is a curve. So z is equal to fxy naught represents a curve in 3D. Okay. Now you can treat this z is equal to fxy naught as similar to our one variable function, because z is dependent and now this z depends only x, because we fixed y as y naught. Okay, now we can find the derivative using our normal formula. So that derivative is defined as partial derivative. That is called partial derivative because here we find the rate of change of f with respect to x alone by treating y as a constant. Now we fixed y as y naught. Okay, then what is the formula of evaluating the derivative of a single variable function? Yes, this is the formula for evaluating dy by dx at x naught for a one variable function. Limit delta x tending to 0, f of x naught plus delta x minus f of x naught by delta x. The numerator is change in y, denominator is change in x. So this is our ratio. Okay, so what is the analogous definition for evaluating the derivative at x naught for this particular function fx y naught? There is no change. The only difference is here y naught is a fixed number. Now this is only a function of x alone. You can treat this as a function of x alone. So what is the formula? Yes, its formula become like this. Limit delta x tending to 0, f of x naught plus delta x comma y naught minus f of x naught y naught divided by delta x. Okay, so this is the rate of change of our function fxy at x naught y naught with respect to x alone. Okay, this derivative is called partial derivative of the function f with respect to x at x naught y naught. Okay, and we can denote this derivative by this representation fx x naught y naught is a suffix x. So this suffix x stands for the derivative with respect to x, and or we can write like this dou f by dou x or dou z by dou x at this point. Okay, these are the only representations for this partial derivative. Similarly, you can define partial derivative of f with respect to y at the same point. How? First of all, we are going to substitute x equal to x naught. That means intersection of this surface and x equal to x naught. X equal to x naught is a plane. So intersection between this surface and plane is again a curve. Then you can differentiate along the curve. The curve is nothing f of x naught y. So what is the analogous formula? This is the analogous formula, d by dy of f of x naught y at y equal to y naught is equal to limit delta y tending to 0 f of x naught comma y naught plus delta y minus f of x naught y naught by delta y. This is the rate of change of the function f with respect to y, denoted by like this. So here instead of here we use only d, normal d. Instead of d, here we use a curved d. This is called partial derivative. Okay, so this partial d stands for this function depends more than one variable. That's all. And dou f by dou y stands for this y. This y stands for this derivative is with respect to y. Otherwise, the rate of change of f with respect to y alone. That's all. By treating x as a constant. Okay, this is the geometry of our derivative fx x naught y naught, the partial derivative of f with respect to x at x naught y naught. So first step is, first we substitute y equal to y naught. Now z is equal to fx y naught is a function of x alone. Geometrically this represents this blue curve because y equal to y naught is a plane, this blue plane, and z is equal to fxy represent this yellow surface. So its intersection is nothing, this blue curve. You got it? Now this is like an ordinary y is equal to f of x. Then we know that what is the derivative of y is equal to f of x at a particular point. Analytically, it represents slope of this tangent. So this is the tangent at this point for this curve. Then our fx x naught y naught represent slope of this tangent. Okay. Or analytically, this derivative represents rate of change of z in x direction, right? In x direction at x naught y naught. You got it? So we have two interpretations for fx at x naught y naught. Okay, next we consider fi of x naught y naught. Okay, my question, what is the equation of this blue curve? Yes, z is equal to, yes, this blue curve is the intersection of our surface z is equal to fxy and the plane x equal to x naught. So that is nothing, z is equal to f x naught y. So this is the equation of this blue curve. Next we are going to differentiate z with respect to y using our normal formula of derivative. That gives the rate of change of z along y direction. This is the direction of y, right? Along y direction at x naught y naught. And geometrically this quantity, this derivative represents slope of this tangent or rate of change of z along y direction at this point. Okay. Okay, so together you can see that one gives a rate of change of in this direction, y direction, other gives the rate of change in x direction at the same point x naught y naught. Okay. Okay, consider a function z is equal to fxy. Then similar to our previous definitions of partial derivative at a particular point, you can define the partial derivative in general. Okay, so in general, dou z by dou x is equal to fx xy. So here it is clear that this derivative is with respect to x. So automatically we can treat y as a constant, that's all. It doesn't substitute any value for y, but underlying idea is we keeping y as a constant, that's all. So limit delta x tending to 0, f of x plus delta x comma y, this y is same, minus f of xy divided by delta x. That means the numerator is change in function f, change of function f with respect to x alone. That's the idea. Okay, by delta x. So this limiting value is our partial derivative with respect to x. Clear? So similarly, you can define the partial derivative of z with respect to y using this formula. Here, the numerator is the change in function f with respect to y alone divided by delta y. So this gives the partial derivative in general. Consider a problem. Find fx13 and fy13 for a function fxy is equal to 2x cube pi square plus 2y plus 4x. First we are going to solve this problem using our basic formula. Basic formula means actually we have to find the rate of change in the direction of x. So you can treat y as a constant. So we consider the intersection of the surface with the y equal to 3. Okay, so first we are going to consider z is equal to fx3. That's a curve, right? So what is fx3? By substituting y is equal to 3. Yes, so our z become 18x cube plus 6 plus 4x. Okay, this is like a curve in 3D. Next you have to differentiate this with respect to x using our normal derivative formula. So what is dou z by dou x? Yes, its derivative become 18 into 3 times x square. 6 becomes 0. This is 4. Okay, so its derivative is then. So what is fx of 1 3? To find fx of 1 3, we have to just substitute x equal to 1 in this equation. That is 54 into 1 plus 4, that is 58. So this is the partial derivative of f with respect to x at 1 3. Similarly, you can find this fi of 1 3. How? First we consider z is equal to f1y, because we have to find the rate of change with respect to y alone at 1 3. So we keeping x as constant, x equal to 1 at that point. So what is this? So what is fy or dou z by dou y? You simply differentiate this expression with respect to y. So this become 2 into 2y, that is 4y. This become plus 2 and derivative of 4 is 0. So we have to find actually fy of 1 3. So what is fy of 1 3? By just substituting y is equal to 3. So that is equal to 40. You got it? So this is our rate of change with respect to x. This is the rate of change with respect to y at the point 1 3. Yes, answer is 58 and 40. Consider the next problem. Actually, this is our same problem as first one. Same problem. Only difference is here we are going to solve this problem in second way. Second way means first we are going to find the partial derivative with respect to x by treating y as a constant. That's all. It doesn't depend. Does not substitute y is equal to 3 or something like that. We just assuming y is a constant. Then you simply differentiate with respect to x. Then we substitute the 0.13. That's it. Our second method. Okay. Okay, so what is our fx? Fx means you simply differentiate this expression by treating y as a constant. That's all. So you can think about this 2y square is a constant, like a number. So what is the derivative? Yes, that become 2 into 3x square into y square. There is no change in y square. That's a number, like a 2. Clear? Plus, what about the derivative of 2y with respect to x? Because now we are treating y as a constant. So its derivative is, yes, 0. Again, its derivative with respect to x, that is 4. So this is the derivative of this expression with respect to x by treating y as a constant. By simplifying this, we have, now it is very easy how to find fx 1 3. You simply substitute x equal to 1 and y equal to 3 on this derivative. This is general formula of partial derivative. Okay, so this become 6 into 1 square into 3 square plus 4. Okay, yes, this is same as R58. Similarly, you can find the derivative of f with respect to y by differentiating this expression by keeping x as a constant. So what is the derivative with respect to y? Yes, 2x cube is a constant. So this become 2x cube into derivative of y square, that is 2y, and derivative of 2y with respect to y, that is 2, plus derivative of 4x with respect to y. Now this x is a constant. Okay, so this becomes 0. So this is the derivative. Next, you simply substitute 1 3. Then that gives fy 1 3. So that is 4 into 1 cube into 3 plus 2, that is equal to 40. Same as our previous case. Okay, so we can find the partial derivative in either of these two ways. Better, this is more easy to evaluate. First, you simply differentiate the expression with respect to x by treating y as a constant. Then you substitute the point. Okay. Next problem. At fxy is equal to x square y plus 5y cube. Find the slope of the surface z is equal to fxy in x direction at the point 1 minus 2. Similarly, we can find the slope of the surface at this point in y direction, the same point. And how to find first one? How to find the slope of the surface in x direction? Mathematically, what is that? Is it fx or fy? Yes, it is. It is fx, partial derivative of f with respect to x at the point 1 minus 2. Okay, similarly, what is b? B is the slope of the surface at this point in y direction. So we have to find the rate of change of z with respect to y alone at this point. That is nothing, that is fy of 1 minus 2. So first we have to find fx and fy. Then you simply substitute these 2 points. What is fx? Yes, fx is the derivative with respect to x with respect to y as a constant. So 2x into y, its derivative is 0, that is 2xy. So you can easily find fx 1 minus 2. You simply plug these values in for x and y. So 2 into 1 into minus 2, that is nothing, minus 4. So this is the slope of the surface at the point 1 minus 2 in the direction x. Similarly, you can find fy. What is fy? Fy is nothing. Yes, the derivative of this with respect to y. Now x square is a constant. So this become x square plus what is the derivative with respect to y? That is 15y square. Then by substituting 1 and minus 2, you can find this derivative at 1 minus 2. So this is equal to 61. So derivative is in the direction, the slope in the direction x is minus 4. The slope in the direction of y is 61. So fx is minus 4. That means what? Derivative is negative means the function is decreasing, right? In which direction? X direction. More precisely, this is our curve. Z is equal to fx minus 2. This is exactly the curve. Actually, the direction of this curve is x direction. Okay, this curve is decreasing the rate of 4 units per unit increase in x. That's all. Okay. Similarly, what is the interpretation of this fy? Fy is 61 means Z is increasing at the rate of 61 units per unit increase in y. Clear? Okay, consider another problem. Find the slope of the sphere x square plus y square plus z square equal to 1 in y direction at the point this and this. Okay, these 2 points are belongs to this sphere. And it is clear that we have to find the partial derivative with respect to y. That is clear. But there is a problem because we know how to find the partial derivative, but our function should of the form z is equal to fxy. This is a explicit form of the function z is equal to in terms of xy. But here this is not the case. Here a relation between x, y, z, it is not equal to z equal to fxy form. So to find our normal derivative formulas, we have to find z is equal to fxy. Okay. Okay, to find its explicit form, we can solve for z. That gives two separate equations. Z is equal to square root of 1 minus x square minus y square. Other one is z is equal to minus square root of 1 minus x square minus y square. Okay, geometrically, what is this first one? We have seen in first lecture. This is nothing. This is our upper hemisphere, right? This is our upper hemisphere. And similarly, what about this one? This is our lower hemisphere. And it is clear that here z value is positive, here z value is negative. That means this point is belongs to the upper hemisphere and this point belongs to the lower hemisphere. Clear? Then how to find the derivative from this expression? First of all, we have to substitute. First of all, we have to differentiate this with respect to y. Actually, it's a complicated expression. This is z equal to square root. So actually this point is belongs to upper hemisphere. So to find the derivative at this point, first of all, you have to differentiate this expression and substituting the corresponding points. Similarly, to find the partial derivative at this point, you have to differentiate this expression and substitute the corresponding x and y. Okay, so that is more complicated. So here actually relation is not explicit, it's an implicit relation. So we are going to apply a new technique that is called implicit partial differentiation. Okay, implicit derivative, similar to our ordinary one variable function. How? Also, what is the geometry? Geometrically, suppose you consider the surface with y equal to 1 by 3, because we have to find the derivative at in y direction at this point. Okay, sorry, not y equal to 1 by 3. We have to find the derivative in y direction. So we consider the intersection of the surface with x equal to 2 by 3, right? And what is x equal to 2 by 3? It is a plane. So what is the intersection of this sphere with this plane? It should be a circle, and these 2 points belongs to the same circle. Okay, I will show you the geometry. So this is the geometry of this problem. This is our surface sphere, and the sphere intersection with the x equal to 2 by 3, that's give a circle. So we have to differentiate along this circle. Actually, we have to differentiate along this circle in y direction at these 2 points. Okay, so how to differentiate this expression implicitly? The technique is same as one variable case. Here we are going to treat z as a function of xy, right? And keeping x as a constant, that's all, because we are going to differentiate this expression with respect to y. So we keeping in mind that x square is constant, no, sorry, x is a constant. We can we assume that x is a constant and z depends x and y, but now z depends y, right? So how to differentiate implicitly? So what is the derivative of x square with respect to y? That is 0. What is the derivative of y square with respect to y? That is 2y. Then what is the derivative of z square with respect to y? Now you can treat z is a function of y alone because we keeping x as a constant. Yes, its derivative is 2z into derivative of z with respect to y. That is nothing, partial derivative. Dou z by dou y. Right? This is equal to 0. The derivative of 1 with respect to y. Anyway, 1 is a constant with respect to y. So this is the expression. By solving this expression, you can find dou z by dou y. So what is dou z by dou y? Okay, here 2 is common, you can cancel, and this become like this. Then dou z by dou y is equal to minus y by z. Okay, now our partial derivative is in terms of y and z. Now you can easily find what is the derivative at this point and this point. Okay, at this point our y value is 1 by 3 and z value is 2 by 3. So what is dou z by dou y? 1 by 3. So at this point derivative is minus 1 by 3 by 2 by 3, that is minus 1 by 2. Clear? Dou z by dou y at this point is equal to, here y is 1 by 3 and z is 2 by 3. So it is minus 1 by 2. Similarly, you can find the derivative at this point. So at this point, the derivative is minus 1 by 3 by minus 2 by 3, that is 1 by 2. Clear? Okay, so at this point, derivative is negative. That means the curve is decreasing. That is true because here in y direction, our curve is decreasing. Clear? And at this point, our derivative is positive. That means our curve is increasing with respect to y in this direction at this point in y direction. Okay. So that is the geometrical interpretation of these derivatives. Yes, minus 1 by 2 and 1 by 2. Okay, this is your homework. Thank you.